Now that we've set up the boundary layer equations in both differential and integral form, we're going to look at ways that we can numerically solve these equations. This will allow us to look at general geometries as opposed to the simple geometries that are useful for analytic solutions. Today, we're going to talk about laminar boundary layers, specifically incompressible laminar boundary layers. And next time, we'll talk about turbulent boundary layers. So the method that we'll discuss today is Thwaite's method. Again, it's for incompressible laminar boundary layers. I'm going to go through this in a little more detail than some of the others in terms of derivation because it's something we'll use on the homework. So what I've plotted here is our normal boundary layer plot, right? Normally, we actually plot it this way, right? Y, U, and it looks like as follows. I made both of these look the same, sorry. This is Y normally, and this is U. Normally we plot the vertical distance going away from the wall, but I've turned it on its side because we want to look at the slope and the curvature, and it's just easier to do it in the natural mathematical way. So that's all I've done is just turn things over on this side, right? This is the edge. Okay, so first of all, let's look at the velocity gradient at the wall, du dy at the wall. All right, that's this slope right here. And as we've discussed, that's of course related to our shear stress. It's directly proportional to that shear stress. In this method, I'm going to say this is proportional to some quantities that we have. So what are the things that we have that are natural scales? Well, the only real velocity scale we have is this edge velocity. So we'll use that for our velocity scale. And for our distance, we could use a few things. We could use displacement thickness. In this case, we'll use momentum thickness. These two should also be, of course, be related. All this is saying is that if I increase my edge velocity, for example, I take this dashed line and move it up, that's going to affect the slope. And of course, if I affect the height, right, the height of this boundary layer, so as this has a more gradual slope or a steeper slope, that's also going to affect this initial slope. So I have this proportionality. And one of the assumptions of Thwaite's is that we can make this an equality by assuming a linearity, that this is just going to be multiplied by some unknown constant L. So L is a scalar. We just don't know what it is yet. It's just a parameter that we're going to put in here to make this proportionality an equality. We're going to do the same thing now for the second derivative, right? So let's look at the curvature of our boundary layer profile at the wall. And again, this is why I drew it on the side, because it's easier to see, right? I can see this is a positive slope, for example. And the curvature here typically is going to be negative for a healthy boundary layer. So I'm going to put a negative, use the same scales I had before, right? So this is a velocity scale, and since the second derivative, I've got to divide by 2 lengths, so I'm going to put 2 thetas here. So the boundary layer does not have to have positive curvature. That's just going to be the typical case, but it could. I remember the positive curvature is the frowny face, right, looking down, but it could also have a positive curvature at the wall. It could, for example, look more like this, right, and then come up, right, which in this case would look something more like this. But we can see that as that's happening, right, as that curvature becomes more positive, it's flattening out here at the wall. And once this becomes flat, then the flow is separated. So an increasingly positive curvature is an indication that we're approaching separation, whereas the negative curvature, the more negative it is, as this becomes even more negative, like so, right, a steeper boundary layer, that's even healthier. I have even more velocity towards the wall. I'm even less likely to separate. So we can see already that this curvature parameter here is important in helping us to kind of judge the health of our boundary layer or how close it is to separation. We'll do the same kind of thing here, a similar assumption that there's a linearity assumption. And so we'll multiply this by another constant, a different constant, lambda, and also an unknown scalar, but just to make this an equality. I'm sorry, I should have before here wrote a proportionality, right? Okay, so those are the first things we're going to do. Let's now jump over to our boundary layer equation. This is the one we looked at last time. But specifically, let's apply this at the wall, right? So this equation applies generally within the boundary layer. But let's go all the way to the wall. And at the wall, we know that the velocity is 0. We have a no slip condition. So these terms are gone. And this term here, the second derivative, is going to be applied at the wall. So we'll use this expression that we have right here. Okay, so let's plug all those things in. So now I've got 0 equals my edge velocities. Those are just inputs. And then I have a minus, because this had a negative curvature, a minus nu times VE over theta squared times lambda. And again, remember, nu is my kinematic viscosity. So I have this expression at the wall. We could rearrange it now to solve for lambda, for example. So lambda is going to be theta squared over nu times dVE dx. And that's useful because remember, lambda was one of those unknowns, right? It's something that we just insert in here as an unknown to make that proportionality inequality. But now we have an expression for it. So that's great. I'm also going to just rearrange to solve in terms of dVE dx, because we're going to need that later. And that's lambda times nu over theta squared. So nothing new there, just rearranging the variables in different ways. Okay, so let's also look at the integral form of our equation. This is that momentum integral equation for a boundary layer. We now have an expression for this term, dVE dx. We're going to use this expression, but we now need to get an expression for CF in terms of our other variables. And you can probably guess where we're going, because remember that this is just a normalized shear stress, and shear stress is related to our velocity gradient, which we have an expression for. So if we go back to the definition, skin friction coefficient is just our shear stress, just a normalized shear stress. So we divide by a dynamic pressure, and normally we'd use the edge velocity. So by definition, the shear stress is our viscosity times our velocity gradient at the wall, and then we divide by 1/2 rho the edge squared. Well, we can see that this is now our kinematic viscosity, and this term here, du dy at the wall, we have an expression for assumption form right here, right? So let's plug all those things in. That gives us let's see, we'll bring the 2 to the top. I think then we've got a new v edge squared, and then du dy was VE over theta times L. So this is VE over theta times L. Assuming I did all that right, one of the VE's cancels, so I get 2 nu L over VE times theta. Okay, so that's great. So what I'm going to do is I can substitute in this expression for CF. I can plug that into here, and then I can take this expression here, and I'm going to plug it in right here. Okay, so I'm just going to make those substitutions, and we'll just do that here on the next page. So actually I can, yeah, we'll do it on the next page because I'm going to need a little room. So let's see, I've got 2, actually the 2's cancel because there's 1/2 there. So we've got nu L over theta VE equals, this term remains, d theta dx, and then I substitute in for that dv dx term. So I'm just trying to get everything, I'm just trying to get one equation that's in terms of all these new unknowns that we've created, right? This lambda and this L. Let's just get them all in one equation here so we can relate them. All right, so I've got them all together now. So we're going to move them all to one side, right? L and lambda, I don't know what they are, so I'm going to put all of them on one side. Just algebra, so I'm going to kind of skip those steps and just write the result here. Again, all I'm doing is moving my unknown terms to one side. So over here on the right, I've got my L's and lambdas. This is going to be L minus lambda times H plus 2. All right. So what Thwaite did then is he looked at this right-hand side and he plotted it for different values of lambda, do some experimental data. And this is what this curve here is on the right. What we're seeing at this parameter M is actually our lambda. And what you might notice from this from this plot is that it's fairly linear. Noticed a remarkably good, linear relationship. And so this is a data fit now. And based on that fit, we saw this right-hand side was about 0.225 minus 3 times lambda. And we notice again that it's linear, so it seems to depend only on lambda. And what that suggests then, right, is that must mean that H must just be a function of lambda and L must just be a function of lambda. So that'll be important later. But for now, we've got an expression that we can use. We're going to rearrange this a little bit. We want to solve for d theta dx because that's going to give us an ODE. So let's do that. Let's just rearrange this equation in terms of d theta dx. That's going to give us d theta dx equals 0.225. That's one of those constants from that empirical expression. Nu over VE theta minus 3 times lambda times nu over VE theta. Okay, so one more step here is we've got this lambda, but remember lambda is not something that we really know much about. So we've related it here in terms of variables that we do care about. So let's substitute that in. And that's going to give us our final expression for our ODE. D theta dx equals 0.225 nu over VE theta minus 3 theta over VE times dVE dx. Okay, this gives us a first order ODE that we can now solve. So if we look at this equation, recall that the edge velocity is an input, right? We get that from our inviscid solution. So if we're solving for the flow around some geometry, we've already computed what the edge velocity is everywhere around that, right? That's the tangential velocity around the geometry from our inviscid solution. So because we know VE, we can also get this derivative. And remember, we're using boundary layer coordinates, so X just follows that curvature there. It's just how does the edge velocity change as we go around the boundary layer. So these are all inputs, and nu as an input as well, right? Often in the form of a Reynolds number, but we need to know our input condition. So this is just a ODE that we can solve for theta using any of our favorite ODE solvers. So in our process, we're going to call this step 1, right? And step 1 is going to give us theta. We can solve for theta. So at the end of this step, once we plug in this ODE, we're going to get theta, right? This momentum thickness height as a function of X, right? So we can now plot this. We can look at our boundary layer thickness, or at least our momentum thickness as it varies along the boundary layer. And we can do this for an arbitrary shape here because we can plug in the edge velocity that corresponds to our shape. All right, so step 2 then, that would be it if all we wanted was momentum thickness, but we're going to want to get displacement thickness and skin friction coefficient things, so we got to keep going. So step 2 is now that we have theta, if we go back, we can see that, well, now we can easily get lambda. So I'm just going to write that again. So step 2 here is just simply compute lambda now that we've got theta. And so lambda is going to be varying along our boundary layer. Before we go on, let's take a moment to think about the significance of lambda, even though it's just this constant that we don't really have a physical significance for. If we go back and look at it, it's the proportionality constant for a curvature. So remember that a negative curvature is an indication of this healthy boundary layer. It's actually going to erase this boundary layer. So if lambda is positive, that means our curvature is staying negative. And the more positive lambda comes, the healthier this boundary layer is, right? It's fuller towards the wall. The opposite is true. As lambda becomes negative, that means we're getting a positive curvature and we're approaching separation. So that'll be, or potentially transition. So that'll be an indication of separation or transition, as we'll see. That's just something to keep in mind for right now, is that lambda will be an important parameter for that. And if it becomes too negative, then we're going to predict separation, or for our purposes, we'll predict transition. All right, so step 3, now that we have lambda, recall that we determine from this fit that must mean, since this whole thing just depends on lambda, that both L and H must also just be functions of lambda. That's not something we can derive because, again, this came empirically. So these are other empirical fits. Here is one such set of fits. I believe this is from Sabici and Bradshaw. But these are just some piecewise fits for lambda. We can compute L and H. So this is our step 3. We get L and H. We're also going to say that if lambda is less than minus 0.1, right, so that goes below this fit. Remember, that's bad, right? That means our boundary layer is becoming more vertical at the wall, right? So our slope is becoming 0 in terms of du dy. It's about to separate. So that's going to be an indication of separation or transition. And for our purposes in our homework, we're going to use transition. We're assuming it's going to transition. Notice that these fits also don't go past 0.1. So we're going to say if lambda is greater than 0.1, just to use the value at 0.1. So that would just be a maximum. This is an increasingly healthy boundary layer, but we won't make L or H any different from the value right at 0.1. Okay, so now we've got L, we've got H. If we have H, you might think, well, what can we do with H? Well, let's see, step 4, let's recall what H is. H is just a simple ratio of our displacement thickness to momentum thickness. So we can now compute our displacement thickness. So we can get that along our boundary layer. So we can plot both of those thicknesses. And finally, step 5 is our skin friction coefficient. And we've already got an expression for that, but we now have the variables it depends on. Here it is, right? CF is this thing. So let's write that again. CF equals 2 nu L over theta VE. And again, this is little CF, it's our shear stress. So if we wanted, now we could get the skin friction drag on our boundary layer just by integrating this along the boundary layer. All right, so we have everything we need. Actually, though, to solve the ODE, we need one more thing, which is an initial condition. There are 2 types that we'll have. One is starting from a free end. So it starts from 0 and grows from there. And the other is starting at a stagnation point. And at a stagnation point, the boundary layer thickness is not 0. So in this case, it starts from some non-zero thickness, and we have 2 separate boundary layers that we solve, one going on the upper surface and one on the lower surface. In this case, although the initial height is, let's say, 0, that's problematic to start with because we'll have this divide by 0 here, and we won't be able to go anywhere in our ODE. So what we're actually going to do is not start at 0. I'm going to greatly exaggerate the size. We're going to start at some very teeny distance with some very teeny initial height. And so our initial distance is going to be something really small, like say 10 to the minus 6. And because we've gone so small, so short a distance, doesn't really matter what the shape of the rest of the profile is. We can use a flat plate because we've gone so far. So we'll use our Blasius solution, which is an analytic solution for an incompressible laminar boundary layer. And this is something we saw last time, so I'm just repeating it again. But we're going to plug in this very tiny initial distance. And again, that should be a very good approximation, because even if this thing curves and has a velocity gradient and so on, for this very, very tiny distance, it's going to be well represented as a flat plate. For the stagnation point, Moran's textbook has a good derivation that I'm not going to go through right here. I'm going to write a little different format that's in the book, but it looks like this: 0.075 times nu divided by our initial velocity gradient. So this is the velocity gradient at the stagnation point, and then this whole thing is square rooted. So that's our initial boundary layer height, which again is not 0, around a stagnation point. Okay, so we now have everything we need to do this. I won't do this in the video, but this would be a good exercise for you to now try this. A good first test case is just take a flat plate. This Reynolds number is irrelevant. This is just one we did in class, but you could use any one that you like. and compare it to the Blasius solution. Because we have an analytic solution for that, it's a good case to compare it to. In fact, this ODE for the flat plate is really simple, right? A flat plate is we know the inviscid solution. I don't have to do any simulation at all. If I put in some v infinity, that never changes. So the edge velocity everywhere is just constant, and the edge velocity is equal to v infinity. And because it's constant everywhere, this is 0. And so this whole term is going to drop out of my ODE. And this could actually then be easily solved analytically. In fact, even the more general case can be, but I would encourage you to do it numerically for a few reasons. For one, we're going to eventually do this on an airfoil, in which case you can't do it analytically, right? We've got this arbitrary velocity distribution. You have to do a numerical solution. You still actually could do the ODE analytically, but you still have to numerically integrate. But we'll also then add on a turbulent boundary layer, which we can't do analytically. So it helps to get comfortable again, remembering how to do these ODEs numerically. So that'd be a good case for you to try and compare to the analytic solution, and just so that you can make sure you're doing that right before you add on more complexity. All right, next time we'll talk about one approach to solving a turbulent boundary layer numerically.